Well, welcome to night school. If you don't pass that test, you're out of my class. Focus. Focus! Go, 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 go.
I failed, but I'm gonna take it again.
Rated PG-13.
I have a blue house with a blue window. Blue is the color I've often I wear. Blue are the streets and all the trees are blue. I have a girlfriend and she is so blue. Blue are the people here that walk around.
I hear the drums echoing tonight, but she hears only whispers of some quiet conversation. She's coming in 12:30 flight. The moonlit wings reflect the stars that guide me towards salvation. I stopped an old man along the way, hoping to find some old forgotten words of ancient melodies. He turned to me as if to say, hurry boy, it's waiting there for you. Time to do the things we never The wild dogs cry out in the night as they grow restless, longing for some solitary company. Do what's right. Sure, it's Kilimanjaro rises like Olympus above the Serengeti. I seek to cure what's deep inside, brighten up this thing that I've become. Gonna take a ride to take me away from you. There's nothing that 100 men or more could ever do. Bless the rains down in Africa. Gonna take some time to do the things we never
Okay, well, welcome back to 16A. Today is going to be the last lecture that is, primarily in Module 1, connected to the imaging lab and, connected to linear algebra. From Thursday's lecture, we're going to start transitioning, of course, still building very much on all of the linear algebra tools that we've built up, into thinking about more physical devices, and in particular thinking about circuits. So today, given that you have a midterm coming up, I'm going to be introducing a bunch of new ideas, but we're going to do it in a way that actually connects up to everything you've learned before. So everything you will see today is something that you have actually already seen. And all I'm going to be trying to do is trying to review and connect back up into things that you have been seeing before and will help you for the midterm. Our idea is not to try and introduce a bunch of new concepts right before the midterm and then make everyone really stressed out. We're going to try and really, use this to review older ideas. So with that, let's just get started. Reminders again that you have a midterm on Monday. It'll be 8 to 10 p.m. You will be told which room that your midterm will be in closer to the date, probably the morning off. So please make sure you check your email and Piazza. Because it's such a big class, everyone will be distributed in rooms around campus. So you will need to make sure you go to the right room to get your copy of the midterm. And I guess that's really it. Homework is due Friday. Self-grades are due today. And I think that's it in terms of reminders. So one quick thing I wanted to just remind everyone of is a definition, which you guys have seen in discussion, but I just wanted to kind of remind everyone, is the definition of an eigenvector. Which is an eigenvector is, let's say we have a matrix A, then a vector V that is not equal to 0, this is very important, such that A times V is equal to lambda V, is called an eigenvector of the system. We've been talking in lecture in terms of eigenspaces, but an eigenvector is basically a vector in your eigenspace, such that this property holds. And basically it's saying that an eigenvector is something when your matrix acts on it, what you will get out is a scaled version of the same direction. So these are invariant directions. Invariant is a word that you might hear coming up. Basically, when A acts on the vector V, what you get out is just a scaled version of V. Okay, I just want to remind everyone, I shouldn't have to remind people this far into lecture, there's a no tech policy. Laptops, cell phones, computers should be off, unless you have special permission from me. Everyone? Great. Okay. So just now that we have this reminder and this definition, I want to go back to null spaces and talk even more about how eigenvalues and eigenvectors are connected to null spaces. So and again, you'll see that this is nothing new that we're actually going to see. This is something that you've all seen before, but just calling it out. So let's say now we have, again, our two websites, A and B, and they have the following link structure. So basically, of the people on A, a quarter of the people continue to be on A, but 3/4 of the people go to B. And of the people on B, people really like B, so 3/4 of the people on B stay on B, but only 1/4 go back to A. So it's kind of a less extreme version of the Berkeley-Stanford example that we saw. So what is the transition matrix for this? Q is equal to 1/4, 1/4, 3/4, 3/4, right? And all of you have done this many times now. You've calculated eigenvalues and eigenvectors for this. So go ahead, take a minute, and just calculate out the eigenvalues. You don't have to go all the way to calculating the eigenvectors. Just take a minute and, write out the characteristic polynomial and then compute what the eigenvalues are. If you're done, make sure that you have the same eigenvalues as your neighbor. Check your work. How many people are done? How many people need another second? Okay. How many people are done now? Okay, looks like most people are done. So, how did you do it? Does someone want to call it out? Tell me what steps you did and volunteer. Anyone? So, 1/4 minus lambda. So, like, how did we get there? Q minus lambda I. So, what is Q minus lambda I? 1/4 minus lambda. 1/4, 3/4, 3/4 minus lambda. How many people they've seen this enough times now? They understand, right? Okay, so I can start doing this faster? Yeah? Okay, great. So what is the determinant of Q minus lambda I? So this is 1/4 minus lambda times 3/4 minus lambda minus 3/16, right? Which is equal to, according to my calculations, lambda squared minus lambda, which is equal to lambda times lambda minus 1. Is that what everyone got? Yeah? Because the 3/16ths just cancel, right? So now, what are the eigenvalues of this matrix Q? They are lambda equal to 0 and lambda equal to 1. So what we're getting here is this interesting 0 eigenvalue. Right? We've seen in the past where we had an eigenvalue of 1 and an eigenvalue smaller than 1. Right? And then in discussion you saw an example where you had an eigenvalue that was larger than 1. So here, now you have this interesting situation where you have an eigenvalue of exactly 0. So let's try and deal with this. Let's try and understand this. First, let's compute the eigenvector corresponding to just lambda equal to 1. So for lambda equal to 1, what do I have? I want to calculate the null space of 1/4 minus 1, 1/4, 3/4, 3/4 minus 1. Right? If I want to calculate this eigenvector or eigenspace. So if I row reduce this, what do I get? How many people know how to row reduce this matrix? Okay, good. You have a midterm coming up. What is this equal to? Negative 3/4, 1/4, 3/4, 1/4, right? Negative 1/4. So when I row reduce this, what do I get? Minus 3, 1, 0, 0, 0, 0. Does everyone see how I got this? Everyone with me? Good. So, now how do I find the null space of this guy? I have one free parameter. So I say, let's say x2 is equal to t. And then I have minus 3x1 plus x2 equal to 0. So I have minus 3x1 plus t equal to 0. So what do I get as my eigenvector? So the span of, what do I get? This basically means that 3x1 is equal to t. Negative 3? No. One over 3 and 1, or 1 and 3, right? Same thing. So the eigenspace corresponding to lambda equal to 1 Okay, now let's look at the eigenspace corresponding to lambda equal to 0. Right? This is something we've seen and done many, many times before. So if I think about q minus lambda I, when lambda is equal to 0, what is this equal to? Exactly q, right? So what is the null space of q minus lambda I? It's exactly the null space of q. So what you're seeing here is the fact that if a matrix has a null space, that is non-trivial. So it means that you have not just the zero vector, you have more than just the zero vector in your null space. Then you're always going to end up with an eigenvalue exactly of 0. So take a minute, now we've done this many, many times. What is the null space of Q? Talk to your neighbors. Just, quickly make sure you know what the null space of Q is. What do you get as the null space of Q? Just anything where x is equal to y, right? Where the two coordinates, or minus y, sorry. The two coordinates are opposites of each other. Right? This is the null space, and this is the span of the null space. And so, basically, we've been talking about eigenspaces and null spaces, but actually they're just kind of different words for the same thing, or null spaces are a special case of eigenspaces. So, the eigenspace corresponding to lambda equal to 0 is the null space of Q. Yeah, question?
So any matrix with a non-trivial null space is going to have an eigenvalue of 0.
Question was, does any matrix with a non-trivial null space have an eigenvalue of 0? The answer is yes. Any matrix with a non-trivial null space will have an eigenvalue of 0. And why? We're going to see exactly what's happening here. And explore this exact idea a little bit more. So, does everyone see how these are exactly equivalent? Just because here, where is this coming from? It's because Q minus lambda I is exactly equal to Q. There's no magic happening here. It's just the definition. Everything is set up in a way for these things to be equal. So now if I showed you this matrix Q, and I asked you to tell me what the column space of the matrix Q was. What is the column space of the matrix Q? What is this guy? Turns out to be the column space of the matrix Q, right? What is Q? So, if I take any xy and I multiply it by q, I get out basically a quarter x plus y 3/4 x plus y. Right? Which is equal to basically x plus y by 4 times 1/3. So where are the spaces that Q can actually map to? They're all in the span of 1 to 3. So Q is this 2x2 matrix, but can it map a vector to anywhere in R2? So if I take a vector and I transform it by Q, what is going to happen? I'm going to end up with stuff exactly on this line. So can we draw this in a picture? So if I was to draw this out, let's say I have my space, R2. These are my standard bases, E1, E2. Oh. And so, what is this vector 1, 3? And let's draw the other eigenvector. So this is the first eigenvector, lambda equal to 1, V1 is equal to 1, 3. And what was the second eigenvector? Are people following me? Lambda equal to 0, V2 is equal to negative 1, 1. So let's say I take a point, a vector, along the pink line, anywhere, and I multiply it by the matrix Q. So I take this point along this line, and I multiply it by the matrix Q. Where does it go? Is this either too easy or too hard? Okay, take a minute and talk to your neighbor. Where does this point go when I multiply it by Q? Question? While you're at it, also talk about where a point on the orange line would go. So how many people know where a point on the pink line would go? How many people don't know where a point on the pink line would go? How many people know where a point on the orange line would go? How many people are confused about where a point on the orange line would go? It's okay to be confused. Okay, good. So we have some people who are still thinking about things. So remember, what is Q? Q is a transformation, right? Q is taking the space and transforming it. And let's look at the pink line first. What is the pink line? The pink line corresponds to this vector minus 1, 1, right? So if a vector V is in the null space of a matrix Q, if V belongs to null space of matrix Q. What happens when I take Q times V? Where does this go? What do I get on the right-hand side? I get the 0 vector, right? So if I take this vector here, this point, or this vector, I take this vector. Let's call this vector V. Or let's not call it V, let's call it W. If I take this W and multiply it by Q, what subspace of R2 does W lie in? It lies on the subspace spanned by -1, 1, right? What is the subspace which is the span of -1, 1? This is the null space of Q, right? So when I take W and I transform it by Q, where is it going to map to? The 0 vector, right? When I take a linear transformation, it's basically saying take the matrix that represents the linear transformation and multiply your matrix. So all of these points here are basically going to go right to the origin. They're going to go to the 0 vector. What about this point? Where is this point going to go? This point is also going to go to 0, 0. What about this other point here? It's also going to go to 0, 0. Right? Do you see that all of the points along this line are all collapsing into that one point? When I take this when I multiply by this matrix. So now if I told you that, hey, I multiplied some vector by matrix Q and I got out 0, 0. Tell me what your vector was. Can you do it? No, right? Because how many options are there for vectors that map into 0, 0? There's an infinite, right? Any vector along this line would do that. Does everyone understand what we mean by a null space? So let's use this intuition now to understand this orange line here. So what happens when I take... So what is this orange line representing? This is the eigenspace corresponding to... Which eigenspace is this? Lambda equal to 1. So what does that mean? When I take Q times V for a vector V on the orange line, I get out 1 times V. Oops, sorry. Thank you. Yeah, please remind me. I can't really see here. I can't see behind me. So we have basically for every vector V, when I transform it by Q, what do I get back? I get back itself. So now if I was to take this vector along the orange line and I transform it by Q, what do I get back? Get the same vector back. What about this vector? I get the same vector back. This is true for any vector along the orange line, right? Is that clear to everyone? So now we've understood basically one set of infinite points in R2. We've understood a second set of infinite points in R2. What's the third set of infinite points in R2 that we have not yet considered? Everything else, right? So the natural question is, well, what happens to everything else? So take a minute and talk to your neighbor and try to figure out what happens to everything else. Like, where does this point A, B go when transformed by Q? Make sure you talk to your neighbors on both sides. Okay, how many people have a sense of what's going on for a random point? For any point that we choose. So if I choose this point a comma b, what happens when I multiply some point? I mean, I wrote out x comma y here, but same thing, right? What do I get out? Where is this point going to go when Q hits it? The orange line. So if a comma b, remember, okay, let's just call this x comma y so that we match up. X comma y goes to x plus y by 4 times 1, 3. What line represents the vector 1, 3? The orange line. So where is x comma y going to go? Somewhere on the orange line, right? In fact, if you don't want to know exactly where it's going to go on the orange line, it's going to go to x plus y by 4 times this vector. Right? So again, every point is going to go somewhere on the orange line. Where is this point going to go? This point is going to go somewhere here. This point is going to go somewhere here. How many different points are going to go to, like, let's say we have this point here on the orange line. How many different points are going to be transformed to exactly this point? Infinitely many, right? All of the points such that x plus y is equal to this quantity. You see, x plus y is all that matters here. So as long as x plus y is equal, all of the points such that x plus y is equal will all transform to the same point. So now, if I think about inverting the matrix Q, right? Remember, what do we mean by inversion? We mean that if I take the operation Q, then I can get back the previous time step, right? Q goes forward, Q inverse goes backward, right? So if I take a vector and I operate Q on it, I have ended up in one of two places. Where have I ended up? I have either ended up on the orange line, or I've ended up at 0, 0, right? 0, 0 also is on the orange line. So when I take the operation Q, I've ended up on the orange line. Can I go back to where I was before? No. So can we say Q is invertible? No. So how are null spaces now connected to invertibility? If a matrix has a non-trivial null space, which means it has an eigenvalue corresponding to 0, this means that the transformation that Q is applying is non-invertible. Q is not an invertible matrix. Why is this true? This is because of this intuition that you need to be able to go back and forward. So basically, what this is doing, what you're seeing here is a collapse of dimension, right? When I apply the transformation Q, this 2D space is collapsing into this 1D space. Does everyone see the geometric interpretation of that? There's an algebra that we're seeing. We're seeing that the algebra works out, but there's really a physical geometry behind this. We're not just trying to do equations for the sake of equations. Okay, there was a question on the blue t-shirt. Why does it not go to? The question was, why does any general x plus y go to the orange line, and why does it not go to, say, the pink line? So the pink line represents the null space, right? The null space is the set of vectors such that when Q is applied to that vector, it returns 0. The column space, on the other hand, is what the orange line represents, which is the set of all points that can be reached as after Q hits it. So xy, is this clear? Is this matrix multiplication clear? So no matter what x and y is, what subspace is x and y going to end up in? The orange line. So can it end up on the pink line? So you're basically arguing that this argument shows that you cannot end up anywhere other than the pink line. Black t-shirt. Is the null space the set of all x's and y's that add up to 0? For this particular example, that is the case. Why? Because you just computed, right, that the null space is a span of -1, 1. So it's just so happens that the null space is such that x plus y add up to 0. Does this have to be true for other matrices? No, I just made up this example. Make up a different example, you will not have x plus y necessarily adding up to 0. You might have some different property.
Yeah, but what I'm saying is you could use the x plus y divided by 4 term to get the null space?
Absolutely. You're pointing out here that you're getting this null space is embedded into this column space, because if you can see that x plus y is equal to 0, you can get this scaling. But this might not always be true. You might not always have this example happen to work out this way. This is not something that you can think about generally. So in general, don't try to find patterns that are not explicit. Like, work things out from first principles. Black t-shirt. Will things always get mapped to the eigenspace that corresponds to the column space? In general, this need not be true. In this particular example, we have that. But in general, this may or may not be true. We'll touch upon this a little bit later in lecture, but also take 16B to explore this more. Okay, I'm going to take 2 questions. Yes?
In a more generalized context and on a similar note, in general, is there ever a concrete, consistent relationship between the column space and a given eigenspace, or the row space and a given eigenspace?
Yes, there are concrete relationships. There is, we'll talk, hopefully I'll get to the point where I can define what rank means, and you have a notion of rank, that the dimension of the range space or the dimension of the column space and the dimension of the null space are very much connected. If you want, you can read more about this in any kind of linear algebra book. Basically, the dimension of the range space or the rank plus the dimension of the null space will be equal to n, which is the dimension of the square matrix. But we're not going to be talking about this in 16A, and because it's right before the midterm, I don't want to go into details about that. So this will be covered in more detail in 16B, in the second module in this course, as well as in the further classes that you take. Okay, last question, blue sweatshirt. Does the column space of a matrix always correspond to the eigenvalue 1? No, this is not in general true. It just happened in this example to work out that way. You will see in a minute another example where this does not happen. Because think about it, right? If you have many eigenvalues, if you have a 20-dimensional matrix with 20 eigenvalues and only one of them is 1, is the column space going to be a one-dimensional thing? No, right? You'll have a bunch of different things. Okay, I'll take one question there was a question around here somewhere. Yeah.
How do you know where on the orange vector it will be scaled to?
How do you know where on the orange vector it will be scaled to? We just discussed this, right? So where does x plus xy go to? We just computed this. If I have a general x plus xy, where does it go to? Exactly. Okay. So I can come back if we have time at the end of lecture and take more questions of this, but I want to kind of move on because I want to hit some of the hit some other ideas in the rest of the lecture. But basically, Q is a non-invertible transform. And if you think about it, remember, what was Q? Q was this guy, right? Are the columns of Q linearly independent? No. Could you have told off the bat that Q was not going to be invertible? So just, keep thinking back. All of these things are always super, super connected. But let's do another quick example. So I want to choose Q as something really simple, and this will help answer some of your questions. Let's choose the matrix of all ones as an easy example. Q is 1, 1, 1, 1, 1, 1, 1, 1, 1. So, quick question. Is Q invertible? Is Q going to have a non-trivial null space? Okay, so quickly calculate this non-trivial null space. If we want to try and calculate this non-trivial null space, I want to try and do a slightly different way. We can do this in the standard way, but does everyone know how to calculate the null space of Q? Right? Everyone knows how to do this. So let's try and do it in a slightly kind of different way. Let's try and find out the eigenvalues and eigenvectors and build into this the null space. So let's consider the vector v1 is equal to 1, 1, 1. What is this vector? What happens when I take Q times v1? Yeah. You get the sum of the rows. So if I take Q times 1, 1, 1, what is my output? 3, 3, 3. So is V1 an eigenvector for Q? Right? What is the corresponding eigenvalue? 3, right? So just by observing the symmetry here, we were able to guess what one of the eigenvectors was. Okay? So we have this. And now we know that, this is not invertible. So this has lambda 1 equal to 3. We know that there's going to be an eigenvalue, lambda 2 equal to 0, because we know that this is not invertible. Right? So now if we quickly calculate what the null space of this guy is, this gives me just 1, 1, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0. What is the null space of this guy? I basically get x1 plus x2 plus x3 equal to 0. So if I put, I have two free parameters, so I say, therefore x1 is equal to minus t2 minus t3. Let's say x2 is equal to t2, x3 is equal to t3. So I can write the span of the following vector, minus t2, t3, minus t2 minus t3, and then t2, and then t3 as the null space, right? Everyone just said that they knew how to do this calculation. Right? And why am I calculating the null space corresponding to eigenvalue lambda equal to, why am I calculating the null space of Q? Because we know that the null space of Q is exactly the eigenspace corresponding to lambda equal to 0, right? So by calculating this null space, I can get the eigenspace corresponding to lambda equal to 0. But what is now the dimension of this eigenspace? If I consider if I consider this guy, how can I write it? Okay, I'll write it here just so that it stays on the same sheet of paper. Can I write this as the span of two vectors? So, can I write this as T2 times minus 1, 1, 0 plus, oops, I tried, T3 times minus 1, 0, 1. So if I was to write out the null space now, this is equal to the span of minus 1, 1, 0 and minus 1, 0, 1. So now, what are you seeing here? What is the dimension of this null space? Dimension of the null space is 2, right? What is the dimension of the column space of Q? 1. So again, what is happening here? What does this mean? This shows we're not going to prove this rigorously. You will start proving these things rigorously in, later classes, but I just wanted to give you a sense of what's happening. So here, the null space of Q, in the previous example, the null space of Q was one-dimensional, right? But what is the null space of Q here? Two-dimensional. So this means that actually you're going to have basically these two eigenvectors that are corresponding to this value lambda equal to 0. This is an eigenvector corresponding to lambda equal to 0. This is also an eigenvector corresponding to lambda equal to 0. So here again what you're seeing is basically this kind of collapse of dimension. What you have is lambda 2 equal to 0 is a repeated eigenvalue for this particular setup. And if I was to try to draw this, it would be really hard, but I care a lot about you, so I'll try anyway. Let's say I have this three-dimensional thing, and what is the eigenvector corresponding to lambda equal to 3? We can see this is, let's say 1, this is 1, this is 1, so this is somewhere here. And so now, when Q multiplies any vector, where is it going to go? It's going to go along this line, right? What is the column space of Q? It's going to go along this line. And any vector that is a linear combination of these two guys, where is it going to go? It's going to go right to 0. Does everyone see that? So basically, you might not always have that the column space is the eigenvector corresponding to lambda equal to 1. The column space can be a linear combination of different eigenvectors. And last time in class, what we saw was that if you have distinct eigenvalues, then all of your eigenvectors form a basis so that your column space will be actually the span of all of your eigenvectors. Okay. So let's see another quick example. How many people remember the homework problem that was called nilpotent matrices? Right? It was a lot of matrix multiplication, and it was I'm sure some of you felt, wait, why are they making us multiply matrices over and over again? Well, one reason is so that you know how to do them. But the other reason is that these are kind of interesting. So what is this? Consider this matrix A is equal to 0, 1, 0, 0. This guy, if you compute its eigenvalues, again has lambda equal to 0 as a repeated eigenvalue. And you can do this using the standard thing, right? You see basically that you'll have a lambda here, you'll have lambda squared, this will be 0, so you'll basically get lambda squared equal to 0, and you'll have two roots of lambda equal to 0. So now, what is the null space of A? It's basically going to be the span of anything that is 1, 0. Right? This you should again be able to calculate. So if you compute the eigenvector corresponding to lambda equal to 0, you're not going to get two distinct eigenvectors as you did in this case. Here you had two eigenvectors corresponding to lambda equal to 0. Here you only have one. So it really depends. What I'm trying to say is that you shouldn't try and memorize a certain pattern. Just do the calculation to figure out, what is the dimension of the null space, what is the dimension of the column space, and, go back to first principles whenever things get confusing. And so now here, basically, we see that the null space of this is just a one-dimensional thing. It's not necessarily a two-dimensional thing. And now, what is A squared? Just as a quick check. A squared is just this zero matrix, right? So what is happening here? Why is this null space this one-dimensional thing? This null space isn't everywhere. Because basically all this A does is it preserves the second component, but then it kills it immediately. Right? It preserves the second component by moving it, but then kills it. So as soon as you apply A twice, you're killing this component. Okay, the question? Can you clarify what the significance of the dimension of the null space is? The significance of the dimension of the null space is basically trying to figure out what this collapse of dimension is. So it's saying, when you multiply by Q, what is the dimension of the space that is going to collapse to 0? So what part of your subspace, what is the dimension of that subspace that is all going to collapse to 0? Right? So in the first example, everything along that one line, so we had a one-dimensional null space. In the second example, we had a two-dimensional null space. So it's basically trying to understand what set of vectors is going to collapse to 0 and how big is that space. Okay. So we're here, and let's go forward. I'm going to talk briefly about this idea of diagonalization that builds very much on everything you have been seeing so far. Diagonalization is something that is super cool, and this is something that will help you build your foundation for a whole chunk of ideas in machine learning that you might end up taking later on. Diagonalization forms the basis of concepts like singular value decomposition, PCA, principal component analysis, which you will be learning in 16B. And, classes like 188, 189, 127, which are the core classes that will teach you ideas from machine learning, are basically going to take this one idea and generalize it in many, many, many different ways. So if you understand the basic idea of how eigenvalues work in this, simple case where we're thinking about square matrices and easier settings, the same principles will generalize to the classes that you're going to take going forward. So let's remember where we started last time. So we left off last lecture by saying the following, right? If lambda 1, lambda 2, lambda n are distinct eigenvalues, then v1, v2, vn, which are the basis vector, the eigenvectors, or that are corresponding to lambda 1, lambda 2, lambda n, form a basis for Rn, right? We proved this for the 2 by 2 case in the previous lecture. This is true more generally for n. You can prove this using an idea called induction, which we will explore more in classes like CS70. We will not be asking you to prove, we will not be asking for a proof using induction, definitely not on the first midterm. But, just remember that this will be true. Also, I should say that in this class, we're not going to really expect you to know about the details of, repeated eigenvalues. If I get to it in class, I'll get to an example in complex eigenvalues, but we're not going to really expect you to really understand the implications of repeated eigenvalues and what this means. We're going to stick to examples that are easier, where the eigenvalues are either distinct or the repeated eigenvalues are somewhat easy to understand. So don't worry too much about trying to understand the details of what a repeated eigenvalue means, and so on and so forth. You will learn this much more in classes that you take when you go forward. But I just wanted to expose you to the idea so that you know that there's more out there. But don't stress about knowing it for midterm 1. So we know that we have this v1, v2, vn, and we're going to call this a special basis. We're going to call it the eigenbasis. And we talked about change of basis last time. And so let's say x is a vector in the standard basis. And I can express it in the eigenbasis as, let's say, x is equal to alpha 1 v1 plus alpha 2 v2 plus alpha n vn. And so the coordinates of x in the eigenbasis would be alpha 1, alpha 2, alpha n. And we can call this vector alpha 1, alpha 2, alpha n xv, which is x represented in the eigenbasis xv, alpha 1, alpha 2, alpha n. And I should say this, if lambda 1, lambda 2 are distinct eigenvalues of a matrix Q. Okay, so we know that we can do this. We can transform these in this way. So let's consider now what happens when I take this Q times this X. And what we're going to try and explore here is how matrix transformations actually, are related to change of basis. And it turns out that, matrices have they might have a favorite basis. Not all bases are created equal, and you'll see why the eigenbasis is actually a very, very special basis. And there's a lot of value in trying to express things in the eigenbasis for a certain matrix. So if I take this Q times X, I want to understand what happens when I transform this vector X by Q, right? These are the examples that we did in the earlier at the beginning of this lecture. We said, what happens when I try to transform X by Q? Previous lecture had even more examples that didn't involve these zero eigenvalues. But now I want to write this where X is written in terms of the eigenbasis. So what is X in terms of the eigenbasis? This is just alpha 1 v1 plus alpha 2 v2 plus alpha n vn. Right? So what can I say about this further? I want to try and explore how this transformation Q times X appears in the eigenbasis. So I want to try and find out what are the coordinates of Q times X in the eigenbasis. So when we're thinking about eigenvalues and eigenvectors, if you want to do something and you're ever stuck, what is the one equation that you know about eigenvalues and eigenspaces and eigenvectors? Right? There's really one equation that you guys know. Just like there's one way to solve systems of linear equations. You know, the one algorithm that we do over and over again. Gaussian elimination. The one thing about eigenvalues and eigenvectors. Q times V is equal to lambda times V. Right? So if you're ever stuck, try and think back. How can I use this? Where is this going to be useful? Does this connect to what I'm trying to prove or what I'm trying to understand? So do I have a Q times an eigenvector anywhere here? So what is Q times V1? Lambda 1 V1. So what is the first term here? How can I write it out as? Alpha 1, lambda 1, V1, right? And what about the next term? Alpha 2, lambda 2, V2. Alpha n, lambda n, Vn. And now, if I want to try and express the coordinates of this vector that I'm getting in the eigenbasis, what can I do? I want to try and write this now as a matrix vector multiplication where the columns of the matrix are the eigenvectors, right? When I want to try and find the coordinates of something, what am I going to try and do? I'm going to try and make this matrix and try and see how much is each of the eigenvectors scaled by, right? When I want to try and figure out how is a point expressible as a linear combination of other vectors, how is a vector expressible as a linear combination of other vectors, I'm just trying to find a linear combination of these other vectors to give me this. So now, if I want to write this in this form, if I want to have this what do I get here? What are the coordinates of X transformed in the eigenbasis? Alpha 1, lambda 1, alpha 2, lambda 2, alpha n, lambda n. Right? XV had coordinates alpha 1, alpha 2, alpha n. In the eigenbasis, what happened to each of those coordinates? They just got multiplied by the corresponding eigenvalue. Right? In the eigenbasis, it was really easy to figure out what happened in this transformation. So, if I wanted to write this out further, I can say, let me call this matrix of the basis vectors, let me call this V. And if I have this lambda times alpha, I can rewrite this in the following way. Lambda 1, I can write a diagonal matrix where I have all of these eigenvalues along the diagonal, and everywhere else there's zeros. So all of this up here is a 0, all of this down here is a 0, and there's only values along this diagonal. This is a diagonal matrix. Times alpha 1, alpha 2, alpha n. Right? Does everyone see this? So I'm going to call this diagonal matrix the matrix capital lambda. And what is alpha 1, alpha 2, alpha n? It's just xv, right? So what is xv as in terms of relation to x? So I know that x is equal to v times xv, right? This is exactly this equation written out. What is V? V is equal to V1, V2, Vn. This is saying, what is the linear combination of the vectors in the set V that gives me X? Right? This is just like, for everyone who's getting confused about change of basis, this is what I want you to come back to. How do I write the transformed vector in terms of the coordinates of the basis vectors? So if V1, V2, Vn are the basis vectors, what is this linear combination? This linear combination is just this matrix V times alpha 1, alpha 2, alpha n. So I have X is equal to V times XV, right? And I know that V1, V2, Vn are linearly independent because I've chosen the case that lambda 1, lambda 2, lambda n are distinct eigenvalues. So what can I write for XV in terms of X? V inverse times X. So now, what is alpha 1, alpha 2, alpha n? Alpha 1, alpha 2, alpha n is just xv. But what can I write this as? This is equal to v inverse x. So what is this whole thing equal to? This is just v times lambda times v inverse times x. Pause and digest this. I'll wait for a minute. Talk to your neighbor if something is confusing. Make sure your neighbor understands what just happened. If you're confused, ask your neighbor. If you understand what happened, teach someone. It's the best way to learn. Question? Yes, if all the eigenvalues are distinct, the eigenvectors will be distinct. Because they'll be linearly independent. If you have the same eigenvector, they won't be linearly independent. We're not talking about repeated eigenvalues. We're talking about distinct eigenvalues. Okay, how many people feel like talking helped a little bit? Little bit? Not really? Okay, let's go through this one more time. What did I do? Did I do anything complicated? I just did a matrix vector multiplication. How many weeks have we been doing matrix vector multiplications? Lots. What did I do here? I said, let's take Q times X. X, we said, was exactly equal to this guy. And I just wrote X as V times XV. So I have this, and I'm just saying Q times V1 is Q times lambda 1 times, Q times V1 is just lambda 1 times V1. I'm just using this formula. Then I'm expressing this as the product of this matrix V times these values. I'm just taking a linear combination of the columns of V, which is what it means to express something in a certain basis. So I'm saying, let me express Q times X in the basis of the columns of V. Now, I'm saying I have these coordinates, but I want to write them out in a special form. I want to write them out so that I can recover xv, right? xv is something I understand. I want to write this out in terms of things that I already know. So I'm going to split this guy out into these guys. A diagonal matrix and a column vector. Right? Do everyone see that lambda times alpha 1 alpha 2 alpha n is equal to lambda 1 alpha 1 plus lambda 2 alpha 2? Does everyone see that lambda times xv gives us exactly this vector? So now the last part is just the fact that xv is v inverse times x. Right? Which we know from change of basis. So I have v times lambda times v inverse times x. So what can I say about q? So I have basically qx is equal to v times lambda times v inverse times x. So q in the coordinates of the eigenbasis is basically equal to v times lambda times v inverse. Right? Because these x's are just the same on both sides. And what is special about this? What is this lambda? This lambda is this diagonal matrix. So if I wanted to take lambda squared, what is lambda squared is equal to? How many people enjoy doing out multiplications of n by n matrices by hand? One person. Okay, I have work for you. Please come see me in office hours. For the rest of you, what would you like to have? If I told you I have to keep multiplying a matrix over and over and over again, what's the easiest kind of matrix to keep multiplying? Identity. What is something that is almost like identity? So if I have something with only values along the diagonal, I have zeros here and zeros here. When I take lambda times lambda, what do I get? Lambda squared, where I get lambda 1 squared, lambda 2 squared, lambda n squared. Right? Because of the fact that there's zeros everywhere else, only the elements on the diagonal multiply themselves again. So what does this mean? Remember when we started pumps, right? The first thing we did when we started pumps, the question we asked, was what happens when we apply the pumps twice, right? We did the pumps once and then we did the pumps twice again. And you're really, really glad, mostly, that I didn't have a n by n, 100 by 100 pump system on the homework. Because you would have had to do 100 by 100 matrix multiplication out by hand. But now, if I want to find q squared, and I know that q is equal to v lambda v inverse, what is q squared? I can write this as v lambda v inverse times v lambda v inverse. What happens to these guys in the middle? They cancel, so I get v lambda identity lambda v inverse, which is just equal to v lambda squared v inverse. Right? And what is really easy to square? Is lambda really easy to find the square of? So what if now I wanted to do q to the m? I would get v lambda to the m v inverse. So instead of doing q to the m so many times, I can get away with doing only 3 matrix multiplications, no matter how big m is. Because, finding lambda to the m is a trivial operation. I don't actually need to do a matrix multiplication to do this. So what this is saying is that lambda is the representation of q in the eigenbasis. Right? This is really what we're getting at. And what we're seeing here is that writing a matrix out in diagonal form, this is called diagonal form, is very, very convenient in terms of finding out what happens when you apply a certain linear transformation over and over and over again. So what you see here is that multiplying things, taking the power of a matrix, is super easy when you have things written out in the eigenbasis. It's the favorite basis of the matrix for a reason. What you get is basically all you have to figure out is what are the powers of the eigenvalues. Does everyone see what we're doing here? Why do we care about having this form? Because what you're going to see is now that these different eigenvalues in the eigenbasis will tell you how different components and how different vectors scale. So let's say we have a very, very simple example. Let's say we have a 2x2 matrix with, let's say A times V1 is equal to 1/2 times V1, and A times V2 is equal to 1/3 times V2. The diagonal form of this matrix is going to be the following, right? 1/2, 0, 0, 1/3. And what is going to happen when I take lambda to a power many, many times? Everything is going to decay off, right? So now, in the lab where you're trying to have, how many people have done imaging 3 yet? How many people are going to do it the rest of the remainder of the week? Okay, so some of you have seen this, some of you have not. You'll see this in much more detail on the homework. But what the eigenvalues are saying in this diagonal form is it's telling you how much a certain direction is going to be either amplified or attenuated. So in the case where lambda is smaller than 1, any component of your vector in the direction v1 is going to get attenuated. Every time you multiply by a, everything that is in direction 1 is going to get multiplied by 1/2. Everything that is in direction v2 is going to get multiplied by 1/3. And so if you have a noise vector, for example, and you want to make it so that the norm of that noise vector becomes small, what kind of matrix do you want to multiply it by? You want to multiply it by a matrix that has small eigenvalues, because when it gets transformed that matrix, everything becomes smaller. If you have something that you want, so here we're thinking about matrix multiplication from a different perspective, right? It's a different kind of transformation. It's not some transformation that has happened and we're trying to understand it. But in the lab, you're thinking of a matrix transformation as something that you can construct to get the features that you desire. So if you want to have a vector such that when it's multiplied by a certain matrix, it becomes smaller, what kind of matrix do you want to construct? You want to construct a matrix with small eigenvalues. If you want to have a matrix times a vector, make the vector bigger. What kind of matrix do you want to construct? You want to construct a matrix that has large eigenvalues. So these eigenvalues are basically connected to the scaling that the matrix is going to apply along the different directions of your space. And if you have, direction v1 and direction v2, then you will see how the different directions scale differently when they get hit by this transformation. And this is exactly what you're trying to do in the lab. You have this nuisance vector, you have this noise vector that you're trying to get rid of. And so you're going to choose your setup, you're going to choose your measurement matrix such that when its inverse hits the noise vectors, you're going to get as small a norm of a noise vector as you can possibly get. So for those of you who haven't seen this in lab, I hope this helps you understand what you will see. For those of you who have seen it in lab, we have like 3 whole minutes. Where's everyone going? For those of you who haven't seen it in lab, hopefully, for those of you who have seen it, hopefully this will help you understand. I guess I don't really have that much time to go over some of the other examples that I wanted to go over. So if there is a residual question, I'll take a question for the last minute of class. If not, good luck for the midterm, and we will start the next module on Thursday. Question? Any last question? Yeah. I cannot hear you, actually. Anything related to the course content right now? Yeah. Great question. How are we supposed to order the lambda in the diagonal? We're supposed to basically try and have, you have to have the lambdas corresponding to the eigenbasis lined up. So lambdas have to be in the same order as the eigenvectors are.